is Federico Vigolo. We will talk about C-star rigidity, a bridge between coarse geometry and C-star.
Thank you very much. I'd like to thank the organizers for giving me the opportunity to speak here. And I was here also last week. It was great, and I'm sure this week will be just as good. Maybe starting from next one. Well, right. And I want to tell you about the recent work that I did with Diego Martinez. This is about the group theorem of C-star rigidity. And so building on work of several other people, I will say a few more words about that afterwards. And I've given a version of this talk in other places, so some of you might have seen it. So I tried to shuffle the pieces around, just hoping to give a little bit of a different perspective. And so in particular, I'm now doing what I usually don't do. So I don't start by the motivation, but I start by the theorem, and then the motivation I do afterwards. Luckily, the theorem is easy to state, and it says that so theorem A, which is a C-star rigidity theorem, which says that let X and Y be proper metric spaces. Then X is coarsely equivalent to Y if and only if their row algebras are isomorphic. Okay, I will say momentarily what row algebras are and why one should care. Now, just to make sure we are on the same page, I'm saying what is the coarse equivalence because that's easy. And like with his audience, I think probably most of you, all of you already know what the coarse equivalence is, but just in case. So recall that X is coarsely equivalent to Y if there exists a function f from X to Y and a function g from Y to X. And this function has satisfied that for every little r, there exists some big R, so that if the distance between X and X prime is at most little r, then the distance of the images is at most big R. And same for G, but going the opposite way, and then we want that the compositions be close to the identity. Identity Y and G composed F is close to the identity in X. Where close means that in the supremum distance they are close. They are bounded distance away from one another. And just for later reference, this condition here says that F is a controlled function. That these two spaces are coarsely equivalent if there are two control functions, one going from X to Y and one going from Y to X, whose composition is not quite identity, but it's a bounded distance from being identity. And, well, I guess this audience like to remark that if X and Y are geodesic metric spaces, then so then coarse equivalence is the same thing as being quasi-isometric. So for all intent and purposes, every time I say coarsely equivalent, you can think quasi-isometry if you prefer, and I just don't need to keep track of the linearity constants because I only care about the large-scale geometry, and I really don't care about what the precise ratios between the various constants are, so long as everything is bounded in terms of the rest. Good. And now, so this is one side of the theorem. I'm saying that the being coarsely equivalent is equivalent to something else. And of this, well, of every equivalence, there are two implications. And so I guess we'll start by saying, oh, and at any point, do feel free to stop and ask questions. Like, we don't need, no need to be shy. Right. And so the remark I want to say is that this implication in the theorem is very easy. So I did not define what row algebras are, but pretty much by the construction, it is very easy to see that if two spaces are coarsely equivalent, then they have the same row algebras. They have isomorphic row algebras. So this is the easy part, and the converse implication is hard. And that's why we call it a C-star rigidity theorem, because it is easy to see that coarse equivalent spaces are isomorphic row algebras, but it feels like when you go into the algebraic world, C-star algebraic world, you are losing information. But the theorem says that actually no, you are not losing anything, because there is still there is enough stiffness that an isomorphism of row algebras can be used to then reconstruct a coarse equivalence at the level of the spaces. So it is indeed a rigidity theorem.
Can you clarify that point a little bit? So if I want to talk about, say, automorphisms of the row algebras, right? What kind of automorphisms are they supposed to be inducing on this space?
It is an excellent question. Then let me write theorem B. Okay, the theorem B is that, okay, so that again, well, X proper metric space. Then there is this short exact sequence of groups where, so we start with automorphisms of the row algebra. And any such automorphism gives rise to a coarse equivalence. So this is the group of coarse equivalences up to where I identify closed maps, so that it is indeed a group. And this map is surjective, and the kernel of this map is the inner automorphisms. Well, I guess this is a natural short exact sequence, which means that the group of self-coarse equivalences of a space is naturally isomorphic to the group of outer automorphisms of the row algebra.
Okay. And a coarse equivalence, of course, you can't evaluate at a point because it's correct. Okay.
That's why
it's an equivalence class.
It's an equivalent class, and it is really important. One needs to quotient out the innerness. Like there is no way, like there's no canonical way to go this way. So this is not split, I guess we say. If you're given a coarse equivalence, then you can use it to construct an automorphism of the row algebra. But this is sort of dependent on some choices that you will have to make. So. So to go from here to here, you need to make choices, and to go from here to here, well, you want to quotient out the innerness. Well,
Can I ask one more question?
Yes, of course.
And suppose on the right-hand side I do some operation like tensor with the compacts. What does that, can you tell me what that would correspond to on the left-hand side?
So, so if you tensor with the compacts, I don't think you're getting a row algebra.
Right.
Yes, but one thing that it is true is that like this rigidity phenomenon that we develop is more general than this theorem, and in fact here it remains true if you have like a stable isomorphism. So like if you have an isomorphism between this tensor compact with this tensor compact, also you can construct a coarse equivalence. So it's that there is some rigidity phenomenon there that is like the underlying phenomenon is a bit more precise than the theorem. I think that we have not found what is the correct framework to state the right theorem. Like there is a phenomenon that implies this theorem, and what precisely the phenomenon means, I think, is not entirely clear yet. And yes, and I wanted to say a couple of words about the work that came before. So, okay, the row algebras, I'm going to I'm going to define them, so then we are going backwards. I'm going to define row algebras have been introduced by Rowe in the 80s, 90s, and with important contribution by Hickson and Yu, still here. And then the question of system rigidity is fairly natural, and the first real progress here was done by Spakula and Willett published in 13. And they kind of established the route to prove all the rigidity theorems that later followed. And then there have been some very important technical advancement by this group of people in various combinations, Braga, Farah, and Pignati. And then one very important work was done by this combination of 6 authors. And then in 22, then they proved rigidity in the uniform case. So uniform case. I'm also going to say what this means. And Diego and I, we proved the general case in full generality. Also, they were only doing it for bounded geometry metric spaces. We just do it like, we have the complete theorem and we write the corollary that way. So yes, so that is to say that the route to rigidity has been set by the people before us. What we did was like pushing it to the end. So, good. And right, this is the theorem. Now introduce the theorem. So now we talk about some motivation about row algebras. So, section 2. Motivation. And the reason Rowe introduced them had to do, essentially, my understanding is that it had to do with Atiyah's index theorem. And so go very much back, Atiyah Singer. It is a theorem that essentially says that if D is some elliptic differential operator, then one can attach with it 2 indices. So there is a topological index, D, and then there is an analytic index, D. And this is a differential operator on a compact manifold M. Compact Riemannian manifold. Then one can define the 2 indices, and these 2 indices are the same. And this is what the theorem says. And this index is some integer number. It is a Fredholm index of a differential operator. Good. And so this is classical, and it's a great achievement in the case of compact manifolds. And the question is, what can we do in manifolds that are complete but non-compact? Like, I'm thinking manifold without boundaries, but like some unbounded space. And there are problems. So the situation becomes very different. It becomes so different that, in fact, it is not even clear how one can define an analytic index. So how are indices? And it is my understanding that the idea of Rowe essentially was that one can define an analytical index in the non-compact case, but in order to do that, it is healthy not to look for an integer number, but to define an index as an element in a K-theory group. And a K-theory group is like some abelian group, so it is not quite Z, but it is still abelian and nice. And this K-theory group is, well, it's the K-theory of the row algebra. So that's why he defines some sister algebra. He defines a sister algebra that it has like a nice K-theory with which he can then prove theorem in differential geometry. And so what sister algebra is that? Defining is not too bad. So let now M be complete. Riemannian manifold. And your definition, we consider an operator T that is just some bounded linear operator on a space of square integrable functions. To every manifold, we can associate the L2 space of functions with respect to the Riemannian volume. That's a nice Hilbert space. We can look at bounded linear operator in that Hilbert space. And the definition is that T has propagation at most R if, following is true, we have that for every measurable subset A in M, and if we choose some function C that is supported in A, so that is a function in L2 of A, which I see as a subspace of L2 of M. If we look at what is its image under T, then this is supported on an R neighborhood of A. So this is an element of the L2 space of the R neighborhood A inside L2 of M, which in pictures it just means that, so here we have a manifold M, then if we fix some arbitrary subset A, and we pick like a function that is supported here, so here we have F, and then we hit it with our operator T, then we get some other function, T of F, and this T of F must be supported in an R neighborhood of our original set. That is, the operator has propagation R if it moves functions not too much away from their original support. So everything moved within distance R from where it used to be. And with this definition, it's like an easy remark that, of course, like sum of operators of propagation R also has propagation of post R, and also scalar multiplication doesn't cause any issues. And also, if you compose two operators of finite propagation, then you're going to get an operator whose propagation is at most the sum of the two propagations. So that is to say that if we now consider the set of all the operators T in B of L2 that have finite propagation, so this now is a set of operators, and it is closed under, it is a vector subspace, it is closed under multiplication, composition, so it is a subalgebra. It is also closed under taking adjoint, so it is a star subalgebra. So this is a star algebra. And this is nice, so we give it a name, and we call it, this is the algebra of operators of finite propagation of the manifold. Good. Now, star algebras are very good. The only way to make them better is to pick a completion. And so we consider the norm closure of this star algebra. And so now this is a star algebra that is complete, that is, it is a sister algebra. And sister algebras are nice. And this is almost the row algebra. The only thing that, so this is a sister algebra that has a lot of geometric meaning. The one thing that was missing for row purposes is that the K-theory of these sister algebras is actually very boring, so that the row algebra is defined by picking this algebra and making it have an interesting K-theory. So I guess the definition is that the C star row M is the algebras of all the operate, is a subalgebra of this algebra of operators of finite propagation, where we also ask that T is locally compact. This condition we don't care about for this talk, because from from my perspective, at least from the coarse geometric perspective, this is like the nice geometric objects, and one can prove the rigidity. Proving it for this one is kind of like, it's just a little bit harder, and I'm going to be talking about this sort of object for most of the talk. Let me just say about the local compactness condition here, what kind of things it does. So remark. The remark is that if M is compact, so M compact, then if compact means small, so the whole of M is local, so local compactness means that you have to be compact. So in this case, the row algebra of M is the set of all the compact operators. And this is nice because then the K-theory of the compact operators is given by, well, 0 in odd degree and Z in even degree. And so here we recover back the place that we wanted to define indices. And so that in fact, one and row can define the index of a Dirac type operator as an element of the K-theory of the row algebras, and when you apply this to the compact manifolds, you recover the analytical index. And so, reasons to care. Well, the rest is, you can define indices. And another reason to care, which follows from the work of Hickson, Rowe, and Yu, is that the point is that the K-theory of the row algebra is actually a really interesting object. And so, and these three people, they show that one can define, so exist homomorphisms which are called assembly maps that go from a thing that is called a coarse K homology of the manifold inside the K theory of the row algebra. And these are often isomorphisms, like any space with property A, like any sort of amenable space. For any sort of amenable space, this map will be a homomorphism, and this is a great theorem of Yu. So they're often isos. And when they are isomorphisms, then a lot of other things follows. For example, the Novikov conjecture, zero-in-the-spectrum conjecture, Gromov-Lawson conjecture on scalar curvature. So that is the, I said curvature at the curvature conference, and that's their place. And many results. So this kind of ends the motivation, and the point of motivation that so the motivation that I'm doing up to now is saying, well, there are sister algebras whose definition is actually fairly simple, and then if one starts studying the K-theory of these row algebras, then one recovers some very deep information about the interplay between the topology and the analysis of manifolds. And so that then these assembly maps, this assembly map is comparing a topological world with an analytical world. And if you have an isomorphism bridging between different worlds, you can usually put this information to good use, and in fact, you can use it to prove deep theorems in differential geometry and topology. Right. So this is to say that already the K-theory of this sister algebras knows a lot of information, and then the question is, well, how much information does the whole sister algebra know? And our theorem is the answer to that question. It says that the information that is contained inside here is precisely what is the coarse geometry of the manifold. Questions?
Yes, somehow the condition of being locally compact, which you didn't explain what it is, it creates clause of algebra of the sister algebra of finite propagation.
Yes. Yes, this essentially says that if you restrict T to the space of L2 of A, where A has finite diameter, then you get a compact operator.
Ah,
So every time you restrict to something bounded, you get yourself something compact.
okay.
And then if the manifold is bounded, then you get compacts. So it's in a way like this row algebras consist of operators that are locally, like when you look at some little place, then it looks like compact, and then but then you paste them in infinitely many parts, and then it becomes non-compact anymore. Yes, but I'm not saying more about that because it is not relevant for the rest of the talk, because that's somehow it's just something that makes the rigidity harder, but the rigidity is kind of like more contained into the knowing what are the operators of finite propagation. And on that note, I start now I want to start going in the direction of the ideas of the proof of rigidity theorem, and I think it helps if we restrict to a slightly easier setup, that is the discrete setup, that is the uniform case that has been done by this group of people. So I will now discuss what that means. So the uniform case. So what it means is that instead of looking at a manifold and an L2 space on the manifold, we just look at easier things. So we now have that X is a discrete metric space. Think a Cayley graph, something like this, a graph. And if you have a discrete metric space, then there is an easier L2 space, that is, we consider the space of square integrable functions. And now if you have a bounded operator in here, well, we can think of this operator as if it was a big matrix. So T, we can think of it as a big matrix, coefficient x prime x, where both x prime and x belongs to x. So it is just a big x by x matrix of complex coefficients. Okay. And then we draw our matrix. So x and x, and inside here there is the diagonal of x, so the entries that are there, and an operator T has propagation at most r if all the non-zero entries are contained in an R neighborhood of this diagonal. So take a neighborhood. So the propagation of T is at most R if it is supported in here and it is 0 elsewhere. So it's just a big matrix. Okay. And then in this setup, the sister algebra. So that is what is an operator of finite propagation. Then an element of the sister algebras of sister FP will be like limits, like norm limits of such matrices. And so then this sister FP X is also known as the uniform row algebra. Which is in some sense a smaller cousin of the big row algebra.
So and then the locally compact condition would be that you have some kind of decay of the coefficients along the...
Yes, and in this case it is basically automatic because that reminds me, I forgot, discrete and proper metric space. And then it means that if you have an operator that has finite propagation, then it means that each of these fibers will be finite. And so when you restrict it to a fiber, it is a finite rank operator, which is compact. So the local compactness condition becomes void in this case. That's why it is called already this one is called the uniform row algebra, because you don't need to apply any other local compactness things. And now this setup also lets me explain why this direction is easy. And that is here, so just a remark. So that if you now have some bijection, then a bijection trivially induces a unitary isomorphism between the associated L2 spaces. So I get a UF from L2x to L2y. How? Well, we define it on the basis element, the delta function of x. We send it to the delta function of f of x. So we have chosen a bijection between the bases. This is just like an isomorphism by triviality. So this is a unitary. Okay, and once we have a unitary, then we can conjugate by it. So add to f will now be a map from the bounded operators on L2 of x to the bounded operators on L2 of y. We're sending t to t conjugated by uf. And this is also an isomorphism. So nothing done there. And the remark actually says that if f is also a coarse equivalence, then this isomorphism descends to an isomorphism of the row algebra. So it will map the uniform row algebra over X to the uniform maps to the row algebras over Y. So it is a coarse equivalence, then get add UF restricts to an isomorphism from system FP X to system FP Y. And so this is a proof of the invariance of the uniform row algebra up to bijective coarse equivalence, and the general case is not harder than this. I mean, it is a little bit more technical, but essentially this is the idea. If we have a coarse equivalence, then we can choose bases here and find nice bijection between bases of the Hilbert spaces, and then that's a unitary. There's really no mathematics there. The converse is, on the other hand, interesting, and that is what we are going to discuss now. Other questions? How are we doing with time? Good. Section 4. Good. Essentially, there are three main steps to prove the rigidity result. And we start with step 1, which is a spatial implementation. So now we start with some isomorphisms of row algebras. And at this point, with such an isomorphism, I wouldn't know much what to do, because it's sort of like, it's too abstract for me. It's just like some correspondence between operators on the space. So it's kind of like it's a second degree far away from the metric space, which is what I understand. But luckily, there is a classical structure results of sister algebra that says that since these sister algebras contain the compact operators, then such an isomorphism is always spatially implemented by a unitary. So there is a fact, given an iso, then there exists some unitary operator. Yes, now we restrict to the discrete case, so that I can write little L2 and you know what we're talking about. So there exists a unitary operator between L2 of x and L2 of y, such that phi is just conjugation by u. Okay, and from my perspective, this is much better because this was a mapping between operators on spaces, and this now is a mapping between functions, and functions are basically points. I mean, so this is almost a mapping between the spaces. So it has the situation. The problem is now much more concrete, and now can actually try to do some geometry on it, and I don't have to do. I guess the reason why I could prove anything in this direction is that there is no real algebra involved. It is functional analysis. It is understanding linear operators between function spaces, and this is concrete enough that I can work with it. Good, and this was classical, and as I said, like the root to rigidity has been set by Spakula and Willett, so also this was the first step was in their proof, and then there is a second step that is maybe right there. It's a uniformization phenomenon, and it is this step that has a lot of contribution from Braga, Farao, and Vignati. They made some substantial improvements. Well, I guess. So now we have an operator between functions, and we want to use it to construct actually a mapping between the spaces. And yeah, like the easiest, the nicest thing was if the operator was something like this. So if we see that it sends a delta function to a delta function, well, this operator is precisely saying what the image of little x should be. So this would be like an extremely nice operator to work with. And in general, an operator implementing an isomorphism will not be as nice, but we sort of want to find the niceness inside it. And this is sort of done in this uniformization step. So step uniformization. And essentially, the idea is that, well, that operator is very nice, and if we see it as a matrix with coefficients like an y times x matrix, then that operator is going to have like 1 on top of the graph of the function f. So if you can look at which entries are 1 in the matrix, then we are reading what the function is. And in general, it's not going to be as nice, but maybe we can still look at the matrix entries and see like, well, the matrix entries that are large enough are sort of telling us where the function should be. And that is precisely the idea. So we look at so we define the epsilon support of an operator T. So T from L2 of x to L2 of y. This has to be the set of the tokens yx such that the yx entry is large, meaning it's at least epsilon. Good. And this now is a subset of y times x. Let me write it like this. So x times y. X, y, then there is like subset there. And the fact is that if conjugation by T maps the operators of finite propagation on X into operators of finite propagation in Y, then the fibers of this epsilon support are uniformly bounded. Meaning that now if I look at this vertical section, there is a uniform upper bound on the diameter. And this is good, because if we have a uniform upper bound on the diameter, that means that is basically the graph of a coarsely well-defined function. Like we have like a function hidden inside here that is only defined up to this diameter, but since we are looking for some coarse equivalence anyway, we don't mind if it is only coarsely well-defined. So the bottom line is that this fact is telling us that the sup of the epsilon support of T is almost, so well, the graph of a coarsely well-defined function. And that function really is what we are going for. And actually, then there is another remark that it is, well, we're actually looking for a pairs of functions, so one from x to y and one from y to x. But the other one is also very easy to get, meaning that if u is the unitary implementing an iso, then the inverse is just the adjoint operator from L to y to L to x, and we can apply the same function, the same lemma to this adjoint operator, and then we get that the epsilon support of if star, this is almost the function from y to x, and also this is actually just the same as the transposition of the support of u. So that is, if you have a function, if that function has to be a invertible, then there is a natural way of writing the inverse, and it is like pick the graph and pick the symmetric. So the symmetric is the canonical choice of an inverse of a function. And now we say that this canonical candidate inverse is the support of the adjoint operator, and this is almost a function, so which means that we almost have an inverse. And this means that we now have like almost a function going from x to y and one going from y to x, and they are the inverse of one another. So that means that it is essentially an equivalence. But there is the big problem here, so the big caveat. Is that these supports could still be very small. Meaning that they're not actually defining functions, they're defining partially defined functions. So it will be like some blob in the product, but there is, and that blob is looking like the graph of a function that is only defined on its domain. It's not defined in the whole space. If our blob is too small, then we don't have an everywhere defined function. And that is the last step we need to work on. So we need to do show that if epsilon is small enough, implies that these supports are big, so are coarsely surjective. And this is a real issue. Now I want to write an example showing like this uniformization step, I did not write it in a way that it is clear why it is called a uniformization, but the bottom line is that there are some constants flying around and you want to show that those constants depend uniformly on one another. And the way to prove it is by using some Baire-like theorem, and it's a very nice idea of Braga, Farah, and Pignani. And so that by using some Baire theorem, you get to uniformize constants, and once you have uniform constants, then you have these uniform bounds on the diameters of the fibers, which is enough to define partially defined functions, and then the last step would be to make them surjective. Say like the example of what goes wrong. So in all these sort of things relating with row algebras, there is one class of spaces that are problematic, and they are expander graphs, and those in this case, they are the problem. And so we let X be a disjoint union of points, and we let Y be a disjoint union of expander graphs. So here we have the graphs, and here we have the points. And now I'm going to define a homomorphism. Well, so there is from L2 of X into L2 of Y, I just send the delta function over n to a function that is constant on the nth graph. So I pick like 1 of Gn, and then I make it, like, normalize it, root of Gn. Another bottom line is that I send the one function to the function that is constant here, and 0 elsewhere. So this is my T. And it is a fact that relies on Gn being expanders, so Gn expanders implies that is conjugation by T defines a homomorphism from the uniform row algebra of X inside the uniform row algebra of Y. So it does fit the framework of the uniformization. So this wants to define a map, but what is actually the support? Well, the support is just going to be a union for n going from 1 to some fixed finite number, depending on epsilon, of just the product n times Gn, which is very useless, but it is good that it is useless because, I mean, if we were starting with this map at the level of functions, that we just know it sends like the one function to the constant function here, and we try to build a map between the spaces out of it, it is very reasonable that, like, we just know that this point has to be mapped somewhere inside here, but we don't have any reason to choose one specific point over any other, and that is represented here by saying that to the point n, we just know that the image is somewhere in the nth level, and then which one, it's your choice. So this example is telling us that there are star homomorphisms that are implemented by embeddings of the L2 spaces that really don't talk much with the sets themselves. So it is, one cannot construct functions out of it. And so in what happens in the rigidity then really relies on the fact that the operators U we are looking at is a unitary, so it is an isomorphism. And this example is telling us that something really happens when you assume the surjectivity part. So the step 3. Step 3, use the surjectivity of U to deduce surjectivity of the support. And Yeah, and this is to say that there is some sort of like the C-star category and the coarse category don't really talk too well with one another, meaning that this is a nice homomorphism, but this nice homomorphism is not attached with any meaningful coarse map. And like to get a coarse map, one really need to restrict to isomorphisms, because there one can apply this step thing. Good. And maybe I will write what is the key lemma that one have to prove here. And the key lemma, we can sort of phrase it as follows. Fix R, and then exists epsilon small enough. How do you want to say? Such that if this epsilon is not coarsely surjective on Y, and then there exists some subset of X such that, well, if you have a subset that is an easy operator that we can consider that is just restriction to that set, and that is chi of A, and that's an operator that has propagation 0, so it certainly belongs to the row algebra. And now we look at what happens to this operator under conjugation by U. So, U star, and this will be some element in the finite propagation algebra over Y, but we can choose it in such a way that this operator here is not close to any operator of propagation R. So assuming that this thing is not coarsely surjective, so we fix R, then we find like some small epsilon, so that if this thing is not coarsely surjective, then the image of this operator of propagation 0 is not approximated by operators of propagation R. So there is like we get operators of propagation zeros that are increasingly hard to approximate, and this is sort of against the uniformization, which I did not state in such a way that it can be used here, but this is like the key lemma. And I would just like draw one picture of the idea of like what happens here. The thing is that we have the delta functions, delta x, they are going to be sent to vectors, so functions of a y, vx. And the thing that we know on y is that we can pick like some point, little y, that is very far away from the support, from the epsilon support, which means that then these vectors here, for every little x, they will have very, very little, there will be at most epsilon here. So like Ex will be looking something like this, where this is epsilon. But at the same time, we know, well on L2 of y, there is the delta function, delta y, which means that we can get this function here that is very concentrated at this point here, can be arranged as a linear combination of functions that are like very spread out. And this means that there is like some sum, so this thing must be equal to the sum of Ax, Bx. And for any fixed little x, most of the meat in V of x is out very far away from epsilon, and there is only a very little contribution here. But when you pick like the sum of the whole of them, then you get something very concentrated here, which means that along this sum, you're sort of like canceling out all these contributions there. But then the idea is like, well, let's not pick like the sum of all the Ax, Bx, just pick like a subset of Ex's, so that then we don't let it cancel out the part that is outside. So we want to choose some subset of little x's so that the sums of the tails remains large. And then once we have like these large tails there, then we get precisely what we want. That is like the set we're going to look at. So it's a set that has like big tails there, and then like some contribution here, and then big tails there, and that can, and since this is more than R, that tells you that the operator is not R approximable. And I will stop here. Thank you.
Any questions for Federico? None? Okay. And I guess that ends the morning session. So there's lunch apparently in Churchill College until 2, and then at 2 o'clock is the next talk.